Okay, so let's move to an example. Our example here will be modeling of people's height and relationship of height and weight in people. So this is not something like extremely. This is not something extremely complicated. We will, however, focus at the data set obtained by Nancy Howell in the 60s, describing the behavior or the parameters of Kong people. Kong people are an interesting nomadic tribe, which is interesting because they were very isolated population. So using those isolated population, we have a lot of simplification when creating such models. Those we do not have the interactions from the other populations. So from anthropological point of view, they were very interesting. And this is a nice, simple, small data set of weights of anonymous people that we can use in order to create a simple model. So that's why we consider this one. Of course, different data sets are also okay, but this has given us at least a certain practical approach, because this is something that actual real anthropologists do when modeling. So we have the Kang people tribe measured in the 60s. We have a group of people. So let's do some modeling. Okay, so we move to Jupiter. Again, we have what we are really using here is the I have not pulled from the repository. Wait a second, because this is my bad, and I made a bad thing. I made a bad thing because I have the old code from the repository. My bad, sorry. I've checked everything except that. So there will be some more issues here. Okay. So let's see if it will work. Yes, it will work. Okay. Sorry for the delay. We go back to the modeling of Kang people heights, and in our case, what we did here is this is again an adapted code from the last year with certain changes. It is optimized for command stan. It uses my mini package of VDA tools that you can use if you want to. If you don't want to, there's no necessity for that. But it can be useful to some visualization. That's why it's living here. We are again with the ribbon plot function and of course we are using Arvis, NumPy, stats, pandas, stuff like that. Standard situation with Seaborn white style, so the pictures will look nicely, and with the appropriate DPI, so they will be larger. And this is the mania. We are getting data online, so we are getting it from the Richard McElrath GitHub, and we are using pandas to get it, so we are just reading a CSV file from the web. And we focus at the moment, in order to preserve the locality, we'll focus on the adult part of the population. So we have our model that is the Kang people, consisting of smaller people between around 150 centimeters or less, and also with low body weights and their ages. So we are focusing on the adult population that don't have much fluctuation in their height in order to analyze it. So this is filtered data set of around 300 people. So what we are doing here, we start with avoiding the linear regression at all, and let's just focus on the using of normal model. So let's get a normal model and get it working. So it's a special case of linear model with beta parameters fixed to 0. We will start with prior predictive checks, which you should be already familiar with. So we will assign priors for our parameters. We will then, using prior predictive distribution, so generally we will sample from the likelihood functions without any data. We will want to see what kind of data we are expecting from our prior distributions. We'll compare it with real data, so we see that there is no dissonance between them. We want our prior to be much more broad than the actual data, but we want our prior to allow us to obtain the real data. So we have our model which we are compiling. At the moment, there is an issue with command stan, at least on Mac. I'm not sure this is on Windows or not. You can answer in chat if you observe it. If you have blank spaces in folder names, like here, then you have to compile it every time. It shouldn't happen, but I've replicated on 2 Macs, so this is not something that should happen. So that's why I've made an issue for the command stan developers, and we'll see what will happen with that. And maybe it's a Mac issue, I'm not sure, but it makes stuff a little bit slower. However, I have it all run, so I won't be running the code now. Especially that at the moment I'm on an M1 computer, so without the Intel microprocessor, and from what I observed, for example, compilation is unrepresentatively fast. In case of the, for example, Intel processors, it was slower. But let's continue. What we have here is that we compile our model and we get samples from it. What we are sampling here, we are getting 1,000 samples from the from our model without any warm-up. Why? Because it's on only generated quantities models. We have no parameters, so we are not doing actual Monte Carlo sampling. We are just using random number generators from Stan, which are more efficient in a way because they are written in C and not in Python. So, and we get the our simulated values. So we are simulating the height and mean and standard deviation. So as you can see, we are sampling from the mean. Oh, maybe some discussion of prior selection. We are sampling from the mean in order to get the mean with the at least 20. We have, or let's say, we do not have any idea of height of young people without any knowledge. But average height of an adult person is around 178 centimeters. So, at least adult male. And we are giving it a wide normal distribution, giving it a chance to get it between setting a standard deviation of 20 centimeters. So 99% of our 95% of our samples will be between 218 and 138. So this is a very wide distribution. In case of sigma, we have the kind of puzzling exponential distribution with a parameter 0.067, but this is actually the mean of exponential distribution is 1 over the parameters. So in our case, it will be almost 15. So let's say that we want to have our height to be at least 15 centimeters of spread for the normal distribution for the height to have a standard deviation of around 15 centimeters. This is our focus. So that's a positive with average of 15 centimeters. So we sample from this distribution, we get those variables, and we can visualize them using the histograms. And what we are really doing here is those histograms are ordered, and we are overlaying them with our prior distributions. So for our mean, we have the spread of very wide spread between 130 and 230 centimeters. So we have a lot of samples here. Standard deviation is between 0 and 40 centimeters, so it gives us a lot of space, and simulated height locates us in, let's say, a reasonable, most of the samples is at least in a reasonable interval, because we didn't get any or very limited number of negative heights. I think there's a one sample here hidden somewhere, and we have not exceeded actual observed world record of height, which was 272 centimeters. We have exceeded, again, except the one or two samples. This is an issue of using unbounded distribution for bounded variables, that we can always get something not working, but we can filter it later. Also, these are only our priors. Our data will constrain that more in the middle, or at least around the actual value. So getting those parameters is not that terrible. So we can now use our data in order to get the posterior inference. And for our posterior inference, we will create on our new model height 1 fit, which now needs some data. This data is an information of number of data points and the array of n heights in centimeters. Our model parameters will be mi and sigma, because they will determine the relationship between heights and the measurement process. So we keep the priors, because in our previous observation priors are relatively reasonable, and we model estimate parameters mi and sigma, because heights are distributed as normal distribution for mi and sigma. And for each of those we will generate a sample of height. So we'll get the distribution. We are not doing the tests like in Avi's proposed options. We just will generate for each of our samples of parameters. We will just generate one data point. So we won't be trying to replicate the original data set. We'll just for each of the samples, because it's not necessary in this case. So what are we doing here? We have our compiling our model, which compiles without errors. We provide it with the following data points. What requires mentioning here is that for all the arrays provided for command stan through command stan pi, from pandas we need to add the values attributes. So generally it takes our series or data frame slice and takes the data from it in the form of a numpy array. In case of PyStan, at least in the previous version, I haven't checked this PyStan 3, the values of heights are the values of data. You could send the slice of the data frame, and it was converted to appropriate option. In case of command stan, this is not possible. You have to use the numpy array. So our sampling went relatively reasonable using the chains. We are not running diagnostics at this moment, and we get our summary using Avis. We limit ourselves only to mi and sigma parameters, using the stats flag to limit it only to the 94% confidence interval, which will, for clarity of the view, we've rounded up to 2. So what we've did here is we can see here that mi has a very small standard deviation, is generally around 150 54 centimeters, but sigma of the entire process is between 7, 2 and 8. 2. So it is you have around 8 centimeters of uncertainty with some kind of asymmetric distribution. We can observe it using our joint posterior, so we can see how it behaves. So we get samples of mi and sigma, and those mi and sigma are distributed in this way that there's a tight interval of 1 centimeter on the, or 2 centimeters from 133 to 155 and 0.5. You have a, excuse me, you have the tight distribution here and a bit wider distribution in the scale of sigma of 1 centimeter, at least sigma of 1 centimeter. So we can now compare our observed height to the predicted height, and this is not terrible model. Let's be frank. It gets a bit underway. It doesn't get a spread as much because it's a bit lighter here. It gets outside of the spreads somewhere here. But generally, it's not a terrible model. But certainly, we can do better. We can do better. We want to do better. So we want to get our observed height versus the predicted height and see what's going on. So, how we can improve our model? And natural expansion of our model will be adding a predictor. And adding a predictor is a very simple task because we just want to include weight as our predictor of height because it generally makes sense. Heavier people, like taller people, should be heavier than shorter people in this if they're in the same, let's say, body weight or BMI ratios, right? And in the case of young people, the population might be tending toward overly skinny, but not to have the obese people. So we should have those differences nicely covered by this situation. For the purpose of modeling, we will be using the centering. Why is that? Because we want to have some kind of easier interpretability of our parameters, and we want to have we just take our weights measurements and we remove the mean from that. So we will get the centered values of mean. So that weight of 0 corresponds to an average weight. Why is that useful? This is useful because it is easy to interpret that our intercept coefficient of our linear model so alpha coefficient will be the average average height for the people of average weight. So if people are average weight, the predictor takes a value of 0, and only this intercept corresponds to the entire relationship. So alpha corresponds not to the 0 weight because 0 weight makes no sense, but alpha corresponds to a mean at the average weight. So that's why centering is popular. It has certain limitations because it can get us to some pathologies in certain cases, but we won't be covering it today. So we want to do again a prior predictive checks. Why prior predictive checks are generally something that we should do always or almost always. I'm skipping it sometimes, but rarely, because this is the easiest way to check if our initial assumptions make any kind of sense. Because if our prior predictions do not allow the data to happen, our prior predictions are wrong. Or if our prior predictions are very well motivated, we should check our data. Because something is terribly wrong with data if it's absolutely inconsistent with one another. So it is a tool for checking for our own manual errors, our conceptual errors, and generally model specification. So this situation is very, very similar to the previous one. We have the normal distribution of parameters. We have the exponential distribution of uncertainty, and in our case we change the guaranteed quantities in this way that we are sampling from the our normal distribution n times, because for each data points, or actually for each predictor of weight, we are predicting the height of the So for each of weights, we get one height using our model. So we sample alpha from normal as previously. We assume that average person will have an average weight, and beta for beta we assign normal distribution from between 0 and 10. So model compiles without any issue. We are not using real data. We just provided 50 of samples that are equi-distributed between minimal and maximal observed weight. So of course, the standardized weight. Standardization will be in a moment. So we create an artificial data set for our artificial prior sampling. So we are not the data set, but a predictor set. We create an artificial predictor set that makes some kind of sense, because we want to just cover the entire predictor range. So we are getting the values and see what's going on. And we are not using data too much, because generally this is the problem with all the priors and posterior predictive checks, that there is certain kind of logical fallacy that you shouldn't use data in prior specification, because if you are in the prior specification, then your prior is a function of your data, and then you add the data, so using the same information twice, and you will get an overfit. But on the other hand, sometimes we only have that data, and we have to use something to get some kind of regularization. So be aware, don't care that much. For this purpose, nothing bad happens. If you, however, would take data and you would fit from the data priors, and then again that would be wrong. But if you get, let's say observed range, for example, that's not a bad thing. So again, we are sampling, as always, 1000 samples, and we get our alpha and beta parameters, and we plot them. And what we really have the problem that getting this prior for beta is not necessarily reasonable. This, of course, is a plot returned to the original scale of weight. So we are not using centered weight here, but actual weight. What's the problem? Problem is that our model gets us too large values and certainly too small values, because it can get you very small negative values, and that makes no sense. So this prior for beta is not good. It allows us to get negative slopes, which is generally not that justified, and it's problematic. That's why we will change this prior. This is why we are doing predictive checks. This prior makes no sense. Let's correct it. And we've changed the prior from normal into log normal. Why? Because log normal is distributed on positive values, and this relationship generally can only be positive, and it makes sense to be a positive one. And we've added the sigma of 1, which in a very, very broad case says that we have our sigma corresponds to 1 degree of magnitude. But this is a very, let's say, rough approximation of what's going on. And again, we will do this the same. So we have our model, we just change the beta prior to be a log normal, and we get the our sampling as previously. And this situation is much better, because generally results that we get fit well between 0 and max observed height in history, and we do not get those strange values of low weights resulting in absolutely high heights. So this is this prior is certainly better for this application. So again, changing priors to keep data reasonable is a good idea. To get a prediction reasonable is a good idea. To leave it working. Okay. So let's use ribbon plot to see how our model works, and generally those priors are too broad and they are located too high in practice, but we won't be correcting that here because our data are still within the tails, so they should be able to, especially that we have a lot of data points, they should be able to move our data points to the our mean towards the data points. So let's move to the posterior inference. How our model looks like? Again, very similar. We have only one predictor. We have the data of heights. We have a vector of weights, and we are using transformed parameters here. Why? Because it will be much easier to perform these multiplications here to get the means for each of the heights, instead of doing this computation inside the model. It will be just more numerically efficient. So for each of samples of alpha and beta, we get the vector of mu, and this vector of mu is located where it should be. And after that, we can generate from our vector of mu, we can get our sigmas. This can also be vectorized, but you need to use unit vectors that you multiply sigma by, so you will get enough samples this way. Okay, so there's a model. We create a fit from that model. Compilation works. This is something I've mentioned before. The error that repeats here. This is something for you to check in your free time. Change the number of samples and see what happens when you take that model and get it from in the form of getting it more or less data. Here we are giving it 150 data points. You can give more. I think there's around 300 of them, if I remember correctly. I'm not running it now, so it will be faster. Okay, we get our data fit dictionary. We get it from this data frame. We get right values, and we compute the number of rows. So we'll be able to get the number of data points. Okay. So we fit our model, we get our parameters, we generate the obvious summary for it, and how it looks like? Well, it gets us that the alpha is still very closely, its interval is very close because it gives this average of 153 and with a movement of 0.4 centimeters in one or another way. Beta is the beta, which is here, is the coefficients, and this generally says there's a linear relationship between centered weight and height, and we have managed to reduce the uncertainty of our samples. Instead of around 8, we have now around 6. So it's not that terrible also, with also tighter standard deviation inside it. So if we get our samples, we can look at what are our means. Means here are linear models between weight and height. So for each of samples from me, we get one of the models. So you can see it's located in the center of data. And we can consider this uncertainty from this model by using the ribbon plot. And here we can see that this uncertainty is this uncertainty of our mean. So we just, instead of just getting those samples, we average it. So the assumption is that underlying phenomena that is captured by our model of weight height relationship is somewhere here, which is its mean is the darker path, and this mean has our measurement process or height generated process. These random factors that are added will result in our measurement. So this is the distribution of the weight relationship on the mean of height distribution. So remember, this is not an actual prediction, this is the parameter of the distribution. This is distribution of me as a function of weight. If we want to do posterior predictive distribution, then we need to consider our model, and in this case we get we can see that we have a good coverage of actual data points. Not all of them are covered in this 90% interval, but the question is how much more is there outside. This of course is not a perfect model, but it gives us certain situations, because as you can see the spread here is also visible. So it might be hard to capture something, especially that this is not a general spread for all heights, but it's more located here around this average weight. So it might not be capturable by a linear relationship. And if we can see, comparing the alpha and beta to our priors, we get them much more, get them very tight in order to see here. So if we want to focus, for example, on the selected weight and make predictions of how much such people will weigh, so we can just add it and compute the mean weight for the 50 kilogram range. But in the beginning, we've reduced our data set into the group of adults. But our data set considers also the measurements of the kids. So what can we do with it? We can extend our dataset to get the entirety of it, and we can, in order to simplify the situation, we will standardize this dataset. What does it mean? It's generally the same as centering, but you divide it by original standard deviation, which gives you easy interpretability of, in case of weight, that one value of parameter of 1 says us that the or in other words, it says us that taking a value 1 standard deviation away from the mean results in the value of parameter. So generally it gives us you remove the units from your consideration. You just see that, okay, if our data is away from the original data set, then or from the original mean, then we can add we need to add the number of actual number of parameter, which will, now that we see that the parameter will correspond to the influence of such deviation. So we get new data set. Our standard weight is generally relatively small, so around 1 of the models, and we can then use our previous model in order to compute the data. Because we standardize the weights, we will get different coefficient from beta. It will be larger. Previously it was not standardized, now it's larger by an order of magnitude than previously. As you can see here, here was beta around 1, now it's beta around 20. So, using that, we can see how our model moves, and we can see that we have a systematic problem with our model. This model with new parameters estimated cannot capture the behavior of small weight people, which are well below the standard deviation of the considered population, the mean of the population. So in here we have a spread of between -2 and 2 sigmas, and we can see what's going on with the heights. So this behavior is certainly not linear, but it doesn't mean that we cannot use linear model to capture its behavior. It will be a linear model, however, with respect to parameters. The predictors are generally values of values from some kind of table, and they can be prepared a priori. So we can get weight, and for example we can add a square of weight, which might be advantageous because here evidently we get a curve here. So we can add it here, and we can do again prior predictive checks with our priors here for the second coefficients. For the second order coefficients, we are starting with a normal again, but with log normal for the first order as previously. Excuse me. And our model, again, we can see how our priors behave. Prior predictive checks should be something that we do generally often, and because of that we get our sampling. And this is something I have not to run, but I removed it later to here, and here it works, so there is no issue. Again, the problem is that our prior does not capture everything, but this is normal because the model is more complicated, and simulating data we get the parameters. So setting the actual model, we can now move to again, the change is generally very small. We just add the beta 2 parameter, and we are adding square of weights, which we compute using for loop in the transform parameters. We compile it, we generate data fit, and we predict the height using our model, and we predict the coefficients using our model. Using our model predictions, we can see that it can rather well capture the behavior, but this is generally quantitative modeling, because there is no justification of a quadratic relationship except that it fits. But the fact that something fits doesn't make it logical, or does not make it causal relationship. It just fits and might be used for further applications. So this is something that you need to be aware. Again, we need to get the parameters for it estimated. So here we've provided our dataset in our model in Stan with weight, and we've computed the square of weights. However, this is not the most efficient way, because we can compute the predictors earlier by so-called design metrics, adding square and third powers, for example, to our original datasets, and setting the design metric x as a proper part of our data frame, and in this case will be those last 3 columns. So we are providing it with our design matrix with 3 predictors, so the first, second, and third power of weight, which will fit in our model, again with the same priors, with not any much issue, and sample from it directly using Stan, with assuming again that we have 3 predictors, again using the same as previously spread of values of weights. So using that, we can see that again fitting of third order model is also very possible. However, this time not complicated model creation as previously, but we just use the multiplication of beta parameters, which is now a vector, not a set of 3 parameters, so we get a vector of 3 parameters, and we multiply by a design matrix x, which we provided by from here. Okay, going further along, we can see how it all works and how it concludes. We get the parameters of all those power functions, and this is a start of creating design matrices, which is generally important in the context of all regression analysis, because we are